Hello, welcome to the stream. Apologies in advance. We got some printer going on here in the background, so it'll be a little bit of noise for the first few minutes. Um, Today we're going to start a new series. I'm pretty excited about it, and thank you for your feedback on what to do next. What we feedback in the Discord. So today we're going to start rewriting an old library of mine. And just to get to know how old I am, I wrote this library in 2009, a whole 17 years ago, approximately. But I was a little bit naive back then, and we talked a little bit about that on the end of the last stream. But let me give you an overview of what this library is. And in the meantime, I'm going to make sure I have the latest Gleam, because we're going to use Gleam today, as we have been. 1.18.1 came out yesterday, in case you missed it. So, okay. So Neotoma is a parser generator library. So think of things like Yak, or in Erlang there's Yecc, Y-E-C-C. Basically, you give it an abstract description of the language that you want to parse, and you give it a set of rules to transform what it detects. Hello, Kythera. Welcome to the stream. So you give it a set of rules for how to transform what it parses, and then what you get is some code that will read the concrete syntax of your language and give you an AST, or whatever you wanted to transform it to. A simple demonstration that we can do probably in the second or the third episode, if we do well today, is that you can write a whole calculator where the transformation of your AST will actually give you the result of the calculation. So that might be useful for some tests. But today we're going to focus. I wanted to try to do this like we did the Essentials of Compilation book. We're going to start from very simple foundations and build our way up, and try to make very contained, small transformations. And then hopefully what that will do is kind of avoid some of the traps I got into when I first wrote the library. So, of course, we're going to do it in Gleam. I feel like the type safety of Gleam is going to make this worth it. And maybe if we find that compatibility with Erlang is super important, then we will make some accommodations for that later. And I don't know what those will look like yet, but we might do that. So here's what I'm going to do. I'm tempted to put my reading glasses on today. I feel like I need them, but we'll see if I can do without, because I know that there's sort of a reflection thing going on when I put them on. All right, so let's have a look at. We'll have a look at the original repo, and we'll talk a little bit about the decisions that were made there, and some of the things that were problematic. All right, so I've got Gleam updating in the other window. So, okay, so this is I believe this is the current stable version, or there might be 1.7 stable. You see, I tried to rewrite it before. Didn't go so well. Some of that has to do with there are fundamental flaws in the way that it is constructed that were not straightforward to fix. And I also tried to implement a lot of the optimizations from the research that surrounds this. So anyway, so packrat-parser generator. So if you're aware of parsing expression grammars, they're pretty popular because they're easy to understand. Versus context-free grammars have some more restrictions to them. Packrat-parser generators are the canonical type of parser that you use. I'm sorry, packrat-parsers are the canonical type of parser you use for a peg. And the reason is that pegs require backtracking, but they have ordered choice. So the packrat part, it means that it memoizes intermediate results. So if you, for example, have in your language an if-then-else, and you have a rule that parses the if-then-else, and its second alternative is just if-then with no else, right? So the packrat part lets you parse the if-then part, and if the else part fails, you don't have to redo all that work for the if-then because it's memoized. So that will be a goal of ours, and we may get to that. We'll have to see how far we get and how this turns out. I haven't fully designed this rewrite yet, and my printer's still going. Give me just one moment. I need to make sure it doesn't fill up the tray. Okay. All right. So this is the original. One of the things that I thought was good was that it did the whole thing in a single pass. That's not necessarily a good thing. It's preferable to make your generator a bit more complicated so that your parsers are more efficient. I think that's probably what I should do for the next pass. But we can look at, for example, we can look at the metagrammar. And my apologies, this is a bit small. There we go. That's better. So the original Neotoma is self-hosted. And I went through a lot of pain to get to that. But essentially what happens is I hand-coded the parser the first time. And then I used that to parse the grammar and generate the parser for the grammar. So it's sort of a little circular and it gets a little bit confusing. But at this point, it is self-hosting. So if there's some things that it cannot do. There's some aspects of the metagrammar you cannot change because it's self-hosting. In that you could add new things, but there's some flaws you can't get around. Let me just put it that way. So basically what happened is I got to the point where I had this handwritten parser, right? And it could parse this grammar, and then it could output a parser that parses this grammar, right? Because this is a grammar about the grammars. I call it the metagrammar. But what happened is, we'd get this prop list out. Prop list in Erlang is just a list of tuples with atom keys. This should have been a struct, let's be honest. Anyway, so this essentially defines that the top level rule in this grammar is called rules, and so the set of things in a grammar is the rules. And so there's a sequence of declarations, and then there's an optional code block at the end, and that code block becomes code that's just injected into the module. Like you can think of like utility functions, things you want to factor out. And I think that what might be better to show is a grammar where we actually used it. So this is a project called Cuttlefish. It's pretty old at this point. But hello, Renatius. But this is one that I wrote with my colleague many years ago. It uses Neotoma. Um, so looks like they've changed some of this such that it allows you to get files out of script archives. Um, so, but basically, this file it looks like a sysctl configuration, right? This is the language that this is parsing. So it's like any number of lines. All of them are optional. And then the lines are, the individual lines are settings and or includes or comments or white space. And you see how we can kind of build this up. So a setting is a key separated by white space potentially equals a value separated by white space and maybe a trailing column comment. And you see what we're getting out of here is key value. And this is setting function that's being called here is, so this is a list comprehension. If you haven't seen it, Erlang has list comprehensions. So this is setting, filters this list. It's just a little Boolean returning function. Okay, and then here for keys, you have to have at least one word, and you may have any number of dot separated words that follow it. So you can see how this sort of metagrammar gives you the space to express concepts by building them up recursively. And a value is basically like we have negative look ahead in the grammar, so that bang means there's not this particular capture group here. I say capture group. It's not. It looks like regular expressions, right? It's not exactly regular expressions, but this is saying that there's nothing ahead of this position that is either white space or a line change or a comment, and then just accept anything. So basically anything can be, and it needs to be more than one thing, right? You can't have empty on that line. And then it just takes the, because this is going to come out, this particular construct is going to come out as a bunch of nested lists, where this dot will match one character. And so we just flatten that into a binary. I got it perfectly. Oh, good. Cool. And I didn't even roll my R that hard. Oh, okay. So then this is like, this is just saying if characters to binary returns an error, then like we've got an error where, this is like in a different character set. It should be UTF-8. Okay. And then comments are just like you can put hash comments in this syntax, and it's just any white space, a hash, and then anything that's not a line return. That is a comment, and so this is just becomes the atom comment. And so you can see if we, I'm gonna skip over some of this stuff. Okay, it looks like they added includes at some point. But if you go down here, this is the Erlang code. So this percent is the Erlang syntax for comment. So it was useful, I use backticks up here, but it's useful to also put them in the comment brace because that can be detected easily, and you can just skip it until you have a close comment brace at the end. Anyway, so this is setting function that you saw in that list comprehension above. It says if it's white space, it's not a setting. If it's a list containing white space, it's not a setting. If it's a comment, it's not a setting. If it is anything else, it is a setting. And there's a bunch of stuff with trying to unescape dots that are in there. And then what you can see here with these tests, this is if-def test is conditional compilation in Erlang, the if-def. And this test is only set when you're running eUnit, right? So the contents of this are, hey, read this file, use the module that we're currently in, parse that as a file, and then check that the output is this. So you can see what happens here is you get a list of tuples where the first element is a list containing individual strings, and the tail is a string as well. Or I'm sorry, the second element of that tuple is a string. All right, so, and then there's a bunch of other things like here, just parse something directly, like looking at tabs in white space, making sure that things don't get messed up with tabs that follow new lines, for example. Okay, so this is the sort of thing that we're going to do, but we're going to rebuild it from the ground up. So let's go back here. This is the metagrammar. We will potentially refer back to this at times, but there are elements of it, like I mentioned, that are flawed, and I'd like to fix those, as well as just relearn this stuff, right? So we will be kind of building this metagrammar, but we're going to build it up from the ground up. So things that we're going to focus on today are terminals. So there's the anything symbol. So this is just a quote around a dot. So the quote just says this is a string. You can use single or double quotes. And the dot is anything. It means any character. Now what you'll see here, this code is kind of weird, right? Because how the generator worked was by building up code as strings or binaries. And it didn't use the syntax module that's available in Erlang. That was somewhat for expediency, but it was also from naivete. Okay, there are some other things here that are maybe not so interesting, but this tilde, and you can see it down here, this means don't perform any transformation. So you can see here code blocks in this metagrammar and in all the grammars, they are fed a single variable, or there's a single variable bound in the scope of the expressions of these code blocks, which is called node, and it's a list of everything that was matched in the rule. So in this case, you can see, code can be, this curly brace or a comment curly brace, and then followed by a comment close curly brace, or it can be backtick and then all the stuff followed by backtick. And then what we're doing is we're matching on that. And then finally, the last thing it could be is the tilde string. So like what we've seen up here, right? So if this is the tilde, then we just the code that we're generating is just return the node. So you can see how this gets a little bit circular and can be a little bit confusing. But this is just saying there's no transformation on this. If it's something else, then you extract. So this is labels, which we'll probably encounter later, like several episodes ahead of this one. It lets you put a tag on this so that the thing that comes out that this is labeling comes out as a tuple of the label and the thing. And so we are extracting, we're using propolis to get that tagged thing out of the list. Okay. And then there's a bunch of stuff with escapes, and we'll have to deal with that. And then there's just a bunch of code in here that is incidental. It's kind of like I worked around the limitations of my design by just dumping a bunch of code into the generated metagrammar parser. It's like tracking. So I didn't define the combinators anywhere, and I wanted to avoid the, oh, this function is unused warning. So I kept track of, I say combinators. We'll talk about that in a minute. I kept track of which combinators were used in a ets table, and then only included those ones that were going to be used, um, which is just a mess. It ended up not being the right way. And then there was also an issue of, well, we passed your function these variables, but you didn't use them because what happens is each of these, let's go back up here. Sorry. Each of these code blocks that you put on the trailing end of a rule becomes the body of a function, where the two arguments are node, which we talked about already, and idx, which is the position within the input. But if you don't use either of them, or you don't use one of them, and then you get a compile warning, and I was trying to suppress that. So we look through here and say, did you use any of these in your Erlang code? Okay, and then there's a lot of this, putting this in here. Should have used a set, but there we are. Okay, so we're going to this is kind of an overview. I can show you some of the more ugly bits if that wasn't ugly enough. So here I also have kept a copy of the metagrammar so that I could restore it. Obviously Git is a thing, but I wanted to be able to do diffs on them. Go, what changed? Did it break anything? So you can see in this one, and we'll look at the includes in a bit. This is the basically the main program. If you run Neotoma and you give it a file name, you can specify what the output module is and where it gets output to, and all this is also included in rebar. So you could put your grammar in an Erlang project, and then rebar 3 could automatically generate the code for you just by finding the peg file. But there's a lot of, hey, run the parser on this input, and then extract all the bits, and then there's, look at this, no, go away, this file write file, and I gave it basically a big string. It's like, hey, take the module attributes we generated and take the code that was at the bottom of the file and take the entry functions, which are like file and parse, and then the rule functions, and then the transform functions, and then the includes, and just dump them in there. Okay, here's the other thing. Peg includes.hurl. Hurl. I love calling it hurl, by the way. Anyway, there's a lot of stuff down here. You can see we do literally writing the syntax of Erlang. It starts with a module name at the top and exports, and then go through all the combinators we used, and it's just this gives me the heebie-jeebies. Okay, we are going to look at this just to, where'd it go? Oh, there's some examples in here too, by the way. The includes hurl. So this is the core of how the mechanics of this parser generator worked, which is I ported or copied, I don't remember where they came from exactly anymore, but a bunch of parser combinators. So you remember in Essentials of Compilation, we used a thing called we used an existing parser framework, and we had it spit out tokens, and then we defined our parser as a sequence of use statements and so forth. Those were a bunch of existing functions that take functions as arguments. And those are typically called monadic parser generators because they um, they have a particular kind of structure that looks like that railway programming thing. Anyway, but it's the combinators is specifically like, hey, I want a repetition of these things is a combinator. Like I want one or more of these things, or want these a sequence of these things, these parsers. Um, and so you build up a parser by composing functions. Uh, and that's what this does. And there's a lot of stuff in here about the memoization, um, which this became problematic as well. It used ets to memoize, which is not great. And then it not only used ets, but it used the old dictionary module in Erlang rather than maps, because maps didn't exist when I wrote this. So it had lots of problems. But if we go down, we can see here that this file is mostly a bunch of if-defs. And that, where I was tracking, you use this combinator in the metagrammar, like, hey, we need the anything combinator. That became a series of defines at the top of the module. And so what would happen is if you use the EOF combinator in your grammar, then it would get included into your generated code, because this is like just like static code, basically. And the optional is like the question mark operator. So you can see here, this takes a parse function and it wraps it in another function. And if this parser fails, then, we return the empty list, and then you don't advance the input and you don't advance the index. And then if you get anything else, then you return that. And then not is negative look ahead. So if this does, this is kind of the inverse, not exactly the inverse, but it says if you call this parser and it succeeds, then that's a failure and you expected not to match that thing. And then, so this fail tuple would be returned in any case. In this parse func type, we can jump up there and look at what that means. It's pretty straightforward. So we're going to be not building a monadic parser generator. What I want to build is something that actually generates the Erlang code that is needed to do this thing. And we'll do that probably with syntax trees rather than this, composing functions. This the syntax trees will have a much lower cost at runtime. And then we'll also be able to possibly think about how to structure it such that we get opportunities to optimize past the initial phase. So like we might be able to look at the thing and be like, we can collapse this. We can apply some of those cost optimizations that are in the literature about measuring what does it take to match this particular syntactic structure, or do we need to memoize this thing? Is it cheap enough to just run it every time we need it rather than memoizing? And we'll also figure out some ways to memoize more efficiently. Okay, so you can see here, like, there's lots of options of combinators here. And here's the label combinator. We talked about labeling forms. And you can see here what happens is this tag on the success path gets added on the tag. That's the result of parsing that syntactic structure. Okay, so the that's what I was originally starting with. And now I want to show you the sort of thing that I started doing, and there's my Gleam upgrade done a number of years ago. And you can see, well, I started to try to do it again 4 months ago. But you can see my original attempt to redo this is 11, 12 years ago. 13 years ago. Isn't that sad? Okay. So you can kind of get a flavor of this is the types. They're not exactly types in the same sense that they would be in Gleam, but these are the sorts of things that we'll need to be constructing. So let's get started. What I'm going to do is we're going to... This is not going to be a fork. You can see a bunch of the things that I try to do, a bunch of the passes. This is not going to be a fork. We're going to do a rewrite. So what I'm going to do is I'm going to say Gleam new and get me the help. Okay. The name is going to be Neotoma, and the path is going to be Neotoma Gleam, so that I don't get these mixed up. Okay. All right. Don't need agent threads. Okay, so we are going to open up the shell here, and we're going to rename this branch to Gleam. This is a full-on rewrite. And then I'm going to add sorry, I need to give it a name. Okay. We're going to fetch origin just so we have the basis. This is going to be a completely new branch, right? So we're going to have all the tags and all that. But this is going to be completely clean. Parsing combinators are not as good in Gleam as people seem to think. Do the memory? Yeah, like that's an actual thing. Memory consumption. There's you know, all sorts of delayed values. And what I want to do is we're not going to generate Gleam code. I still want to generate Erlang code. But we're going to need to make that be more efficient by actually building the structures and putting them together. Okay. So first things first, let's get our project going. And all right, we're building. So this isn't going to do really anything yet, but let's make... We want to make something that parses terminals. So this is sort of like when we did the first chapter of Essentials of Compilation, where we just dealt with integers first. Hello, welcome to the stream. Unlucky Roz, welcome. All right. Okay. Let me leave that. I want to think about what the terminal types are, and we can look at the metagrammar if we need to. But let's just start by making a type. And this is going to be I think one of the things that we're going to have to do is have a position. This is really essential. So we will want to have line and column tracking. This is essential for producing good errors. So this byte is going to be a byte offset. So let's just call it offset. And you'll note that Do I still have the other window open? No, I don't. Let's open Neotoma. Also, I think I did another directory that was an attempt to do the same thing, but you can see here that we had this index struct. I want to call it position because I think that that's more informative. But here it's like optional line and column. I think that we should probably have that regardless. If we're able to track that reasonably. And the old way was you actually had a two tuple and it was line and column and they were labeled, and I don't know why I did that. 2009, what do you want? Okay, so I think that I want to say terminal kind, because I think that terminal is a structure, or it might be depending on the structure of the things that come above a terminal. It might be a variant in some other type, if that makes sense. So if we switch over here real quick, there was, I think I had a type definition for primary, right? So we will probably make a type here that is primary, which is a terminal or non-terminal, or star, which is star is a clean star, so it wraps some other thing, or plus, which is also a clean operator. Optional is the consuming positive look ahead. Assert is the this is actually consuming. Deny is non-consuming negative look ahead. And then label is like how you put the labels around things. But I think that with this label thing, we probably want to be more clever there, in that let's see if we still got the, yeah. So like where we had you know, labels on things, I don't want the label to become like a tag. I want it to actually become a bound variable. I think that that will be more useful. So that you don't have to refer to like, hey, the node. And then what we can do is possibly take, you know, the rule name and turn that into a variable as well. We'll see. Okay, so, and then, you know, we were looking at this. Here's some of my answers, right? So we will have epsilon is interesting. That gets generated in a few cases by some transformations. So let's say there's anything. I remember I'm using this as a type marker, not as a it doesn't have to include the position. We'll have something that wraps it that includes the position. So anything. This is probably, let's start with that. I think this is probably the easiest thing to implement. Well, I say it's the easiest thing. The easiest thing might be a string. Character class is probably difficult. Regular expression just piggybacked on Erlang's regular expressions. I think string might be good, or anything. What do y'all feel like? We'll go down the route of either one of them first. Okay, so we're gonna make a type doc here. within the input stream. Okay. The kinds of all concrete syntax elements. Okay, so what I want to do, and let's just say I'm tempted to go back to Essentials of Compilation and see this approach that they took in the first chapter, because it's been so long. It's been like 18 months since we started that, right? We took the break in the middle to do some games. But let's also put in here string. Right? So you can see that if we do Gleam build, we look at the output Erlang code. And where's your Gleam artifacts? So you can see that this becomes the atom anything or tuple string binary. And these types basically get erased, but these are to help. The interesting thing is they don't become records. So we'll need to think about that, whether that is a problem. I don't know that it will be. But we could also potentially define records for each of these things. I don't know that that matters. Okay. So what our goal here is, we're going to let's build a rule. Wondering how much we need to build. I'm thinking we need a rule which is going to have a name. It's going to be a string. And it's going to have let's look at the metagrammar. So it's declaration sequence, a declaration. Okay, and a declaration is a non-terminal. So that's a non-terminal name. A parsing expression. So we're going to have to define that. And if we look at parsing expression, it's a choice or sequence or primary. So this primary, if we go down, right, is an atomic thing that has either a prefix or a suffix or nothing. And these are the combinator bits. So like, does it have, so we can just say, we can probably say for right now, a primary is just atomic. If we look at what atomic is a terminal or non-terminal or a parenthesized expression. So what we can define potentially, all right, so let's go back up. Parsing expression is a choice or a sequence or a primary. So let's just start with primary. Okay. And then primary so I'm trying to pull out just the essential bits here, right? So remember, a primary has an atomic. or prefixed or suffixed. So the other way we could look at this is it just has atomic, and then these could be, the other variants could be 1 or more, 0 or more, optional, assert, not. Except it wouldn't be not. It would be assert, deny, I think is what I said in the other one. So this is atomic, and atomic has an atomic in it. And I don't think that we defined that yet. So atomic, get down here, is a terminal or a non-terminal or a parenthesized expression. We're only going to allow terminals. Okay, so you can see how this is starting to... So let's say terminal. This is terminal kind, and then position. Position. That's what I wanted to get to. Okay. So, okay, so a rule is what we'll do first, like what we did early in Essentials of Compilation, is manually build up these ASTs. And yeah, and then we'll generate some code, and then we'll see what happens. I think that we can probably get to some simple code generation today. So let's see what we can do. Okay, rules are the define the way that non-terminals are produced. Okay, a single parsing expression. Okay, primary is what did we define it as? Okay, primary is a prefix. Okay, so possibly primary is a sub-expression with optional operators on it. Okay, atomic. Okay. If you're not familiar with this word clean, this is a guy who invented, or one of the guys who invented, the idea of repetition in regular expressions. Okay, so an atomic, what can we say an atomic is? And I went past it. Okay, so an atomic expression contains a single terminal, non-terminal, or parenthesized expression. So this will give us, this will tell us like what the variants need to be in the future as well. And I feel like the reason we have this position on here, and we may need to put positions on other things, we may need to do this factor like primary kind and position. Expressions may need to have them. I'm not sure yet. Rule probably needs... The other thing that we could do also, rather than positions, we could have spans. And maybe... that would be super useful. Cover ranges of positions within the input. Okay. I don't know that we'll need to use that yet, but we might. Um, so it might be better to say this is a span. Yeah. Okay. So I think we have enough here to start thinking about how we might write some code that recognizes a single terminal. Okay. Yep. I'm going to look at our trusty book, and we're going to go back to, so they're talking about abstract syntax trees. And they actually are saying, we don't really care, but this is just preliminary things that people are expected to know. So in their first thing, an expression is a variable or a let. An expression, right? And a program is a single expression. So for ours, so why don't we also define the top level thing? I probably put in here a bunch of stuff that doesn't need to happen yet. But maybe what we'll do is rather than do this, let's just say it's a terminal or an atomic. Say we only support atomics. And then okay, language. So grammar is a grammar, and rules is a list of rules. And what we'll do later is expand this, and I may even like comment these things out that aren't being used, and we can come back to them. Okay, so let's make a grammar. This is gonna be a list of rules. So rule, let's just say the name of this is I don't know, we'll say G. And the expression has to be an atomic. So atomic is a terminal. And what I want to show here is this is going to look like in the input. We're not going to parse this yet. We're just going to construct the AST. But this will be like this. So let's say that's this. Rule, the name is G. Terminal, the kind is a string of Neotoma. And the span, we're going to fake it. So this is going to be a span. The start is position 0 byte offset, line 0, column 0. And the end is position 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Okay. So position 15. Okay. So that's, and there's our grammar. Okay. So what we want this to do is we want this to generate some Erlang code. And if we look at, now we could do maybe an interpreter interprets this grammar, right? let's put that IO line back. We could interpret this grammar, which is going to be super inefficient. Or, because the interesting thing about this is about input, like about IO. And we're talking about extensible interpreters. We don't have overriding. Okay. Right. So then they're talking about the x86 assembly language. So if we can think in terms of the book, our assembly language is Erlang. I mean, it's not assembly language. And the syntax, or rather the semantics of Erlang and Gleam are very similar. So we have fewer hoops to jump through. But you know, this is some of the output. How do we conceive that this would generate, or like what the Erlang code would look like for this? So maybe we can just let's make a new file, and it's going to be Erlang. So I might say module G. So we're going to export. It's just going to take a string, right? And I might say that export, or not export, string takes a binary. And this is going to be critical. I think we need to define these types. And it's return OK. And a term, or error and a term. I say term, that's the any type. Okay, so what do we want this to look like? So we are going to we have no transformation, so what it should return is just the string that matched, right? So we're going to call, the function g with the input, and then we'll say that's the start. Now it won't be span. We'll just say it has a position, right? Because that's the only rule. And if that returns, okay, we're going to call it g.rule. So this function will take an input and the position. Okay, it's not going to be okay. But what are we going to do here? We're basically going to look at input The weird thing about these is we might need an additional branch. There's an aspect of parsing expression grammars where they're greedy. And they will match, if the grammar is specified without particular safeguards. So for example, we could put in here an assertion that we have reached the end of the input, which is basically bang dot. There isn't anything. In which case that would fail. But the default mode is consume as much of the input as you can. Let's start with this. So if this is that, our code generated should be okay. Neotoma, right? If it's Neotoma and rest, I think that there's some other errors here, but we'll find out. We'll make a thing that says incomplete parse. And then if it's anything else, we'll say error. And here's where like a structured diagnostic would be useful, but let's keep it simple for now. I would love to say, hey, we were at position this. Maybe we can put that in there. And we can think about how to this is like if I wrote it by hand, right? We can think about how to restructure this such that we might be able to reuse some things. And I'm just going to say, we'll just say no match. That could be something else. But this is basically our code we should generate. Okay, so we're going to take, this is going to change what we generate, of course. We're going to take this G, or so each rule, we're going to generate a function which takes the input, right? And then we're going to look at what is in the parsing expression. And then for the terminal, we're going to generate a case expression that matches the terminal exactly, or whatever rules the terminal uses to generate. So we might take the terminal kind, and use that to generate the clauses. And then I don't know if this clause will actually be relevant. But like a string, you kind of want the exact match. The thing is, though, if we think about yeah, so I think I want to change this value, because what this should give us, there should be some things that it tracks along the way, but also I'm going to put a tag on that. We're going to get rid of this clause. I think that this is simpler. Let's wrap that in a tuple. Okay, so this is the code that we're going to generate. Maybe we don't even put the position in there. We can do position tracking at a later date. Let's just generate this. Sound good? Okay. Unfortunately, I'm probably going to have to make some FFI right away. So let's make... Let's make a folder. and let's make a file here, which is going to be we'll call it okay, and let's look at skim through this first chapter. And okay, and they're talking about generating prelude and conclusion and yada yada. They talk about building the syntax. So we're gonna actually use, for the first pass, we're gonna use the direct Erlang syntax, but we'll probably have some intermediate representations along the way that'll let us do some more things. And they're talking about all of the different passes. So they do uniquify. We may need to do something like that. They do remove complex operands and so forth. And the C language. Again, we probably won't need as many intermediate forms because the syntax or the semantics of Gleam and Erlang are similar enough. But we're going to learn along the way. Okay, so what I want to do here is we're going to pull up the Erlang documentation, and I'm going to put it over here. Actually, I do have Dash, but I kind of prefer to read the online version. Okay, so we're going to look at, I believe it's in the syntax tools. So this gets us Erl syntax, abstract syntax trees. All right, so they have so you can pass an actual value and get the abstract form of it. We'll probably need to make use of that. We need to look at, we'll call it syntax tree. I think you have to do this. Right? Okay. Concrete. Okay, so that returns is literal. I don't know which ones we're going to use it. We're going to need this so we can take the value of this string and turn it into a syntax tree, right? All right. And Erlang has a lot of syntax. I don't know if you've seen this, but it can get pretty hairy. The other thing that we'll want is print, and there should be something in this module that gives you, is it Erl pretty print? Yeah. So this takes Right, so it takes we can format the text of that Erl syntax. So this is going to have so I'm reading. Okay, so this is going to use lists of characters. So maybe what we do, I want to import this. So this is Erl pretty print format. And this takes tree is going to be syntax.syntax tree, and that's going to return we might need to make an FFI because we want this to be to output a string. Yeah. Oh, specify the encoding of the generated file. Interesting. Yeah, let's write a little FFI. Neotoma FFI.erl. And I think that what we're going to do there is it tried to help me there. And this is going to be Neotoma 5. We could put that in syntax, actually. Maybe it doesn't need to be its own module. Yeah, we'll delete this file. Delete. Since I know that I have to make this an FFI module anyway. You're in Sean, how do you know? Well, the thing is, this returns a string. A string in Erlang is defined as a list of characters or code points. There's no equivalent Gleam type, right? So what we need to do, so we're going to say format. We're going to export that. So format takes, you know, a tree, and we're going to say EPP source encoding. So what we want to do here is say like stir is Erl pretty print format tree and then we're going to give it some options, which are encoding. Let's see what that EPP source encoding is. We don't need any hooks. We like the line breaks are fine wherever. Okay, so let's look at the EPP module here, which is going to be I guess I'm gonna have to go back. It's in the compiler. Code preprocessor. I just want to see what that type is. Source encoding. Right, so we're going to say UTF-8. And then we will do Unicode characters to binary stir. Those can be on the line. It just looks long because I have this squished. So you can see the documentation on the right. Okay, so basically we're formatting the syntax tree. We're making sure that it's going to be UTF-8. That means it'll be compatible with characters to binary. And let's look that up. Unicode. We could do list to binary, probably. But if we use the Unicode module, characters to binary, and let's just make this full. So this is equivalent to Unicode and Unicode. In encoding, out encoding. So this is for transforming encodings as well as for taking anything that's a list of characters or a nested list of characters and binaries and turning it into a specific encoding. So we're going to use that. Okay, so what does this give us? So we have format. We can create an abstract syntax tree. So let's make our first test here. Go away, hello world test. We're gonna let's make a new folder. Neotoma and file syntax test. Okay, so this is just testing the FFI, right? We don't need to import Gleam unit. We just need to write the test. Okay, so we're just going to abstract printing test. Okay, so we're going to say, we're going to take and what we need to do is import Neotoma syntax here. And we're going to say syntax, make an abstract form out of that. So it makes it in a syntax tree. And then we're going to say format. And then we'll say assert equals Neotoma. Except this is going to be Neotoma. Okay, so interestingly, it took this and printed out the code points of each character. We might want to think about that. Not necessarily because it's wrong, because it's not. And honestly, I am thinking about, we'll just replace that with this. But it is going to make things a little bit hard to debug. So I wonder if we can go in the pretty printer. And hook. If there's a standard hook that we can use. At the very least, we have confirmed this is going to be annoying to debug, right? But at the very least, we've confirmed that that round trip is fine through the FFI. And if we go here, let me just do this. Copy that. We didn't bring up the Erlang shell. You note that, like I just said, evaluate this term, and it prints like that. So there's got to be a way to hook. Because that's a template. We will want to be using that. Right, because we're going to need to do that. There's a lot of things in here we'll need to use, looks like. Okay. Some of these are just accessors. So note there's an argument and clauses. We can define a function. Definition. Name is a syntax tree. Look at the definition of this type. It's a tree, a wrapper, or all parse. So a tree is a tree wrapper, or it's this Earl parse type. Okay. All right. We are doing this on hard mode, folks. A lot of it is just me bridging the gap. But we have, hey, you can turn anything into a syntax tree. That's kind of cool. All right. And we might have a look at what happens in the Gleam artifacts. Syntax test. So, right. That is interesting. I've never seen that Erlang syntax. Okay, so now, we've changed it to be that. It is interesting what Gleam generates. Okay. We are on our quest still to generate this code. So I think that let's make a folder called pat. Oh, not there. Let me hide the build. That's throwing me off. Okay. So we're gonna make a folder called passes. And we're gonna do something similar to what we did in the other in the essentials of compilation. We're going to need a let's assume that there's all of this exists. We're going to need a pass which is which generates the stuff above it. Right. So we can generate the individual clauses or the individual functions that are the rules. And then we will need to generate this stuff. So let's say let's call generate prelude. And our form here, we will probably so this is going to take something, and it's going to take let's just say it's a rules, or it's like some other form. Maybe we'll have a parser type. So we may need to have this like intermediate representations. For now, let's say it takes a grammar and returns a syntax tree. But it's going to need to take something that is not directly that. For now, this is not right, but I think that we're going to do, this is a list of syntax trees. Okay. Because we don't want the grammar. The grammar is too high level. What we want is a list of functions that have been generated by a previous pass. So let's make a pass that comes before it, which is this is going to be like explicate control. And we're going to want to delay this to the very last moment. Let's call say generate rule functions, or maybe functionize. What do we think? Because I think that what we'll probably do is have forms where we have a rule and then we have a block of code that matches that rule. Let's rename this, because we're going to need why don't we call it generate wrapper? So because we're going to need other things in there too. But for now, let's just say it takes a list of rules. We'll ignore that argument. Maybe we can even just make a little plan here up at the top. So we know that the final phase is going to be generate wrapper. And this is going to take, its inputs are going, or its arguments, let's say arguments, are going to be a list of rules with their bodies. And it's going to output a whole Erlang module. Our goal is to output a whole Erlang module as a syntax tree. The other thing that this might need is injected, or like and this is not going to happen today, obviously, but it might need things like auxiliary code supplied by the user. And there's definitely going to be, we're going to need to include, because one of the things that the Neotoma, the original one, did is it generates standalone modules, and I think that's really important. So utility functions. So we're going to need to have something that like collects what utility functions are going to be needed, that are supplied as part of the library. So this is similar to the combinators thing, but it's going to be more like, you know, advancing the position within the input, like recording spans. And that's something that we'll need to do pretty ubiquitously. But it could be optional. It could be like, well, we don't support, or we don't need the span tracking. We just want to parse this thing. We don't want to track the positions of errors in the input. We just want to say that that it is, you know, just parsed or not. We don't care about tracking the input, because that's something that we would generate at the rule phase, and at the rule generation phase. Okay. All right. So there's an interesting uh say I'll say non-rule auxiliary code supplied by the user. Okay, so this could be like a set of names, for instance. And then we could have static versions of those functions that we parse as syntax. All right. I want to look at the Gleam standard lib for a minute. I wanted to see if there's something in the existing standard lib, Gleam standard lib, that we could use. String tree is sort of that, but not exactly. I was thinking, like, is there something that gives you, there is this 2 UTF-8 code points, but then, or sorry, 2 UTF code points, but then that has a little wrapper struct around it. I don't know that that's worth. And then there's this function, which takes a code point and returns an int. Look at the implementation of these things. Yeah, see, that does an identity. That's interesting. So UTF code point is an int, but it's like opaque. Yeah, on Erlang it's kind of fake. It doesn't, the UTF-8 code point or UTF code point, it's probably just an empty type. I don't even see where this is defined, this type. Interesting. Okay, I got down on a little bit of a rabbit hole there. Okay, so we need to I'm just going to call this convert rules to functions. So this is maybe we call it. So the goal of this is generates an Erlang module from the inputs. Okay, convert rules to functions. Um, how are we gonna? What are we gonna call this? I'd love to call it explicate control, but that's not what it does. Okay, so we're gonna call it functionize. Converts abstract rules to functions. And this is probably going to be continuation passing style because we will want to be able to go through sequences and choices and have them like cascade as cases, right? So arguments is going to be a grammar. Some intermediate form. Um, and I'm going to put 1 here, 2, 3. And its output is going to be list of rule syntax tree pairs. And maybe this needs to have some sort of like name for the intermediate form. A code block from user and a set of utility functions, function names. Okay. The question in my mind is, do we need any other passes? Because I think that we can go in our current format, right? I think we can go from our grammar, our top level grammar that we defined here. So list of rules, right? And because we have limited what we're implementing here, maybe let's just comment out that variant right now. We can deal with that later. We can go from the grammar directly to the list of functions. What do you all think? Let's call this functionize rules. I know, I'm really great at naming things. Hardest problem in computer science. Okay, so we're gonna import Neotoma, and we may need to put this. I think that we need to put these types so that we don't get circular imports here. We need to put these types in a new module. So let's make a new file called grammar. And we're going to put all these types over there. I mean a library with a type called reactor because it reacts. Yeah, I mean, you know, what do you want? Okay. And then, yeah, import Neotoma grammar. Grammar rule. Let's see, as G. Say G dot string. Okay, grammar rule, because I don't want that. Well, I guess it, yeah. These are constructors, right? String terminal span position. Okay, so now all those resolve, and then we won't have that circular problem. So this needs to import grammar. LSP actions. What, what do you think am I? Okay, so so this is going to take our grammar, right? And we're going to have it, as we talked about here, we're going to have it output a list of rule syntax tree pairs. Now, the thing is these are optional bits that we don't have yet. So we don't need to care about those. So right now, it's just going to return a list of rule syntax tree pairs. So we can say this is going to return a list of a string just for the name, and then a syntax tree. Okay. Okay. So now we can go and start to think about what is the transformation we make. So we're just going to say grammar dot rules will list map functionize rule. And we did this a lot in the other one. Okay, so import Gleam list and generate that function. So this is going to take a single rule and return a string, a pair of a string and a syntax tree. Okay, so this is where it's going to get fun. We need to, ultimately we're going to return rule.name and then our tree, right? Okay, so our rule has an expression. Okay, so if it's here, this is easy. So because right now it's an atomic. Okay, so we're going to ignore the span for now. And I hope that there's... Yes, okay, so we can pattern match on that. And maybe what we want to do here is we want to say I'm going to split right, and we're going to look at this, because what we want to do is have it generate we know we wanted a case expression, but there's sort of the idea of, this is where continuation passing style comes in. There's what happens on a success branch and what happens on a fail branch. So I think that what we'll do is we'll say, so we'll match terminal passing kind, and then we want fail. We want this to generate some code. And maybe we have this as a function. And just have it return a syntax tree. Right? And then I think that what we'll do is success is going to take a result, which is a syntax tree, and return a syntax tree. So this is so what we'll be doing is for now that we don't need to pass it, but we will deal with that later. Generate that function. Okay. So I think that it's going to be simple enough to generate the fail case. So let's make the FFI for that. Let me make sure I'm not... Okay, we're going to run over a little bit. But let's look at this module. So tuple takes a list of syntax trees and creates an abstract tuple. Okay, so we want that. So this takes a list of syntax trees and returns a syntax tree. Okay, so we're going to be able to create tuples on both of these. We're going to need to make atoms. I'm tempted to... this is going to do the stuff that we were looking at earlier. So we'll do a string 2 UTF code points. And this be external. There's already type for that. Gleam has atom construction. Okay, but well, let's look at that. Where is it? Gleam Erlang that has that. We might need to pull that in anyway. Let's have a look. Thank you for pointing that out. When it always ends up so small. Okay, so Gleam Erlang Atom. And that's opaque. All right, that's probably better. So yeah, let's, I'm just going to comment this out for now. So Gleam, add Gleam Erlang. Right, we're trying to target Erlang anyway. We might as well have that. Cool. Okay. We don't include string. Okay, so that gives us the ability to construct an atom. We're going to use that in lots of places. The other thing is we might want to do that. If only we could do constants. Yeah, okay. Okay, so what we'll do is we will generate the atom in here. It's not a big deal. Okay, so we're going to say failure, so we're getting there. Syntax is a tuple, and the interesting thing is that, like, this actually is the result type. This. But we can't, we're generating Erlang. We can't rely on the Gleam compiler to lower that. So, so we're going to make, create the error atom. No match is atom create. No match. And syntax tuple is going to be syntax atom of error, syntax atom of no match. Okay, and then success is going to be, we're going to create, and why don't we just pull that out? Right? Okay. That's better. Yeah, so much better. Thank you, Renata. Yes, that was great. Okay, so we'll create the OK atom, and we'll make a syntax atom of that. And then we'll return a syntax tuple of OK and result. Okay, so this is basically, these are basically our things that we call back to. So the core of this is we need to let's look at kind. Okay. And we're going to say, we're going to match literal string is going to be a function. I'm breaking this down very, very small for now, because we're going to have to make use of that later. We're going to want this to be as fine-grained as possible. And I'm going to switch this split to top and bottom, and we'll get rid of the shell. Okay. So what are the elements of this? So if we have a literal string that we want to match on, we need to, ultimately we're going to make a case expression, and it's going to be some clauses. So we need to generate the clauses. We need to generate each arm of each clause. And then we generate the case around it. And that's what we return. So, and ultimately these are going to take functions, which are, you know, the failure function and the success function. But for now, there's just one because we only have one. We can only match one terminal, and it has to be a literal string. Okay, so oh, we could have done char list as well, right? Whatever. Atom is fine because we know we want atoms here. And I believe this atom function can take an existing atom. Yeah, honestly though, you know, OK and error are ubiquitous. This no match, maybe not so much. Okay. Let's look at what we need to do here. Okay, so we need to generate the clauses. So we're going to have a success clause and a failure clause. So let's look at case. Case expression. So the first argument is the subject of the case. So in this case, it'd be a variable. And the second, and then has a list of clauses. So let's go ahead and make this. Let's put this up here. And this is going to be subject. We'll call it is a syntax tree. And then clauses is going to be a list of syntax tree. Let's return a syntax tree. Okay, and then we need to be able to make a clause. So clause has a guard. Oh, okay. So patterns is a list of patterns. Guard is none. Oh, for Pete's sake. We don't need guards yet. Yeah, hi Chris. Welcome to the stream. We just got started today. And I'm trying to do the like very simple first step, and it's already introducing a lot of really interesting problems. Um, but we're trying to be principled about it. Generate syntax trees directly, rather than generating the strings of Erlang source. So okay, so I think a clause. We might make some wrapper functions for this. Um, so there are patterns and then body. Okay, patterns is P1 to Pn, body is B1 to Bm, guard is none. Then it's like these patterns to, okay, so this is a sequence of expressions on the right hand side. Okay, so we're gonna make clauses. Clause. Okay. And this is going to take patterns. It's going to be a list of syntax trees. Okay, and then guard is going to be a list of guards. Guards is going to be a list of syntax trees. And then body is going to be a list of syntax trees. I think that's, there's so much variance because it's untyped, or I won't say it's untyped, it's dynamically typed. The sorts of things you can do in Erlang you can't do in Gleam. We want to limit what we can do. And note here that they say the atom none is equivalent to an empty list, so why don't we just pass an empty list and just be done with it? They also have nested lists here, and I don't know that I want to support that, but that's, you can do conjunction and disjunctions, and I'd actually rather, instead of doing semicolons and commas in the guards, I'd rather use and also or else. I think that's probably clearer, but we don't need to use that yet. So, right. So what we will do. All right. So we need to generate the success clause. The failure clause is easy. So let's say failure clause is going to be syntax clause. I wonder if we need to generate a pattern there. Let's look at what we can do for patterns. There's no thing for pattern. Okay, so we can use underscore. That's useful. So let's export that. TU. I'm not really keeping these in alphabetical order. I probably should. Okay, so that's what we want. We want, I put underscore other, but like basically underscore means any pattern, right? So, and why did I get those in two windows? Okay, so we're gonna make a clause where we use the underscore. Okay, and we have no guard. And then we're going to have it return fail. Okay, so that's this clause. The success clause is harder, but not too bad. Okay, so we're going to say syntax clause. We need to come up with pattern. So the success pattern, we'll put a to do there. We'll put a block to do. Success pattern, no guard. And then we are going to call success with something. So let's look at what we can do to make a binary literal. Binary. Okay, that makes a template. Can we, is there a function that takes literal? There's integer literal. Atom literal. String literal. I mean, okay. So we need to create the stuff for binaries because we're going to be matching on that, right? And again, I'm not really paying attention to what order it's in. So we need binary, which takes fields as a list of syntax tree and returns a syntax tree. Binary field is going to take a syntax tree, or sorry. Yeah, body is a syntax tree. And types is a list of syntax tree. Let's return a syntax tree. Okay, so over here we can go, the literal is binary, syntax.binary. And we're going to say it's going to be binary field, no types, and then we also need to have string. string literal. Let's do 2. Well, let's see. Oh, wait. That's not what I want. It's going to be string, not string literal. The arguments here is going to be chars, I think. Right? Because this needs to be... Yeah. But not representing a specific string literal. You remember when we did this little test here? We took this and did the abstract form. Now we can just do that. That might actually be the best way, rather than this specific string. What does the Gleam Erlang have? We could say it takes a char list. And then we'll say pub fun string takes a string and returns a syntax tree. And we'll just say do string. From string. That weren't confusing enough. Okay. There are other places where we could do this char list thing, but I think that this is fine. I suspect that using something like this, just take the abstract form of a string and use that as a syntax tree, and a binary field might not be happy. So let's do and I need to go back to this. Okay, so we are discovering what we need to do as we go, right? We might just do that. And then we'll make other variants as we need them. I know that we're going to need binary field with types. This is a syntax tree. And then the types is a list of syntax tree. And we might need the size eventually for some things, but for right now we don't. Okay. So we can say binary field here, and we can say syntax string of stir. Okay, so that's the literal. And then the pattern is going to be again, we're looking at this. This is what we want to produce. So we know we need a tuple here. The pattern is going to be this side of the clause. So we want a binary. And then we're going to have this field again. And then we need to make a binary field. And the body of that field, this is with types. Okay. Right, so I'm looking at that one. The problem I foresee here is that we need a particular... One thing this doesn't do is it doesn't say, oh yeah, this produces valid syntax, this does not. That's comprehension. We don't need that. Right, so binary field. Types is the empty list, or okay, if types is a list. Okay, so these need to be class qualifier. No, that's for try catch, right? Because you see class body stack trace. That's not what we want. That's type constraints. Okay, so that's just giving you a thing that produces the type of a node. We may need that later for some analysis bits, but I don't think that we need that right now. Let's look. Okay, so syntax tree is a tree, pattern data, a wrapper, this, or the type of Erl parse, which is up here. Okay, so abstract expression, let's see. Abstract clause is AF clause. Pattern. AF bin. Bin element size, type specifier list. Okay, so type specifier, we're getting there. Type, sign in as entities or unit. Type has to be one of these. Okay. So I think what we should do what I want is this, right? I think what we should do, because we've got type or signedness or endianness or unit. Okay, I'm gonna call it binary. I want to make just this enum basically. Binary field type. And we'll say integer, float, binary, bytes. Why do you do that? Bytes, bit string, bits, UTF-8, UTF-16, UTF-32. And then we will say for now, I'm going to say that because it's not true. That accepts more than these. But if we go Gleam build and things are going to break, but we should be able to see that this syntax, oh, not binary field type, binary. Becomes the atoms that are valid there. However, those need to be syntax trees. So what we're going to do is this is going to be non-public, and it's going to be do binary field with types, and this is going to be a list of syntax tree, and we'll just turn them into syntax trees. I don't know how I feel about that. Like, I feel like it should be easier for us to write that. Maybe this is not necessary. Trying to get to the end here and not take too long. So let's just undo that. Let's make this syntax tree. And we're going to get rid of this. And I don't really need this field, this thing. It is interesting to see the code that gets generated. But what we want here is a variable. So we need to make sure that, and we're in the wrong thing. Because I was looking deep into those types. So variable takes an atom or a string. Okay. pub. Okay, so we're going to make syntax variable rest. And we may want to inject something here where we create unique names because they do shadow. So there may be some earlier phase where we need to like track some state through these, and maybe that's part of the continuation passing. All right, so we need we're gonna have to create the atom again here. So there's the type. Okay, so that's our pattern. Looking back here, we've got this pattern. So we have the literal string as one field, and then we have the variable rest. So I'm going to actually pull this out, and we'll put it here. And then the result is going to be tuple of literal rest. Success result. Okay, so now we have the failure clause. We have the success clause. And I want to clean this up just a little bit. So let's say let success clause, and we'll make it a block. And we're going to move these things up inside it. And we're gonna clean this up a little bit. Okay, so ultimately what we want to return is we want a case expression, not success, syntax.variable input, right? So our input comes from that function, goes there. And then we want the clauses to be success clause, clause and failure clause. And that's the contents of this. Okay, let's simplify this a little bit. This failure clause is fine. That doesn't need to change. The literal, I want to pull this out and say we have the literal string. Okay, and then we have the literal, and then we have the literal string here. And this binary field can take a literal string. We can reuse that. Let's inline that variable. Okay, so we're making a clause, which is the pattern, and the tuple, the success value is a literal rest. Okay, that's better. Okay, so we should see what happens when we generate this rule. And I think that's a good place to stop the stream. So we're going to take this and we're going to pass it to functionize rules. We did this for a while at the beginning of Essentials of Compilation. And then we're going to generate wrapper. And that's going to generate a syntax tree. And then we're going to syntax format. And then we'll IO println. Now this doesn't do anything yet. But what we need to do, hopefully quickly, in generate wrapper is figure out what we need from here. And I think it's like you give it a syntax tree. Yeah, frick it. We're going to 430. Big first stream. Okay, so we want to generate an abstract function definition. So you have a list of clauses. And so we're going to have to construct clauses again. That's fine. Function definition is source code forms. Okay. And then we'll build a form list. So here we're doing a lot of stuff in here. Okay, so we know we're going to need, throw them at the top. We'll sort them out later. Okay, so we're going to need form list. We're going to need function. So form list 1, function 2. We've already got clauses. Yeah. Just when you think you're out, the project pulls you back in. Absolutely. Okay, so let's add form list. And this takes forms is a list of syntax tree. And it produces a syntax tree. And then we have function. Function. This takes name and clauses. So name is going to be a syntax tree. Clauses is going to be a list. Yeah, list of syntax tree. Okay, so we're going to take rules now. Generate function. And then we're going to say that's going to produce forms, right? And then we'll say syntax form list. Okay, so oops. Import that first and then generate that function. Okay. Except this doesn't, our functionized rules produces a list of string with syntax tree. So what we need here is that. And this will take a string and a syntax tree. Okay, so name is Adam from create syntax tree dot 0, right? So we need to create the name of the function. And then we're going to have a clause. Which is going to take so it's just going to take a pattern. And in this case, it's just a single variable input, no guards, and then the body. Okay. Not syntax tree. Right. So it's going to take a list of that. Okay. I thought this was going to be more complicated because the thing is we will need to prepend or append things that are you know, like the entry points. So we won't get this or the module name or the exports, but we will get this. So moment of truth. Look at that, folks. That's what we accomplished today. So we just took our abstract grammar and we generated Erlang code that will match that literal string. I think it's a brilliant place to end the stream. I'm going to make a commit and push this branch. So let's do that and we'll call it. And thank you for sticking around late. Okay, let's make sure tests run. We're gonna probably have to make some tests next time, but we'll say episode 1, generate a function that matches a single string, literal string. This is a good foundation. And thank you for hanging out. Chris, always love to see you. Renatius, always love to see you. And everybody else, thanks for coming as well. And I will see you next time. Have a good one.